Hello, Universe Explorers. Welcome back to Coded Universe. Remember our journey through graphs? Today, we're taking another leap into the world of graphs with shortest path algorithms. These ingenious methods help us traverse complex networks, be it digital or physical, in the most efficient way possible. They're the invisible guides that steer us through bustling cities, sprawling internet networks, and even air traffic. So buckle up, and let's dive into the world of shortest paths. Imagine finding the quickest route in a busy city. Dijkstra's algorithm does just that for graphs, picking the shortest path from one point to another. But what exactly is a graph? Well, in computer science lingo, a graph is a set of vertices or nodes connected by edges, and Dijkstra's algorithm is like a super smart navigation system for these graphs. So how does it work? Let's break it down. Dijkstra's algorithm starts at the initial node, which we'll call A. It sets the distance from A to A as 0 because, well, you're already there. Then it looks at all the nodes directly connected to A and calculates the distance to each. The node with the shortest distance becomes the next current node, and the process repeats itself. At each step, Dijkstra's algorithm keeps track of the shortest distance to each node. If it finds a shorter path to a node it's already visited, it updates the distance. This continues until the algorithm has visited all nodes and found the shortest path to each. Sounds like a lot of work, right? But here's the thing. Dijkstra's algorithm is incredibly swift and efficient. It's like a sprinter who never tires, always pushing forward, always seeking the quickest route. There's one little snag though. Dijkstra's algorithm assumes that all edges are positive. If there are negative edges, it might get tripped up. But for most real-world applications, this isn't a concern. So what's the logic behind Dijkstra's algorithm? It's based on the principle of relaxation. This doesn't mean Dijkstra's algorithm is kicking back with a cool drink. In graph theory, relaxation is the process of making something smaller, in this case, the shortest distance to each node. By continually updating these distances, Dijkstra's algorithm ensures it always finds the quickest route. Dijkstra's algorithm is like a GPS for graphs, always guiding you to the shortest path. It's a powerful tool in the world of computer science, helping us navigate complex networks with ease and precision. Think of Google Maps navigating you through traffic. It uses a concept similar to Dijkstra's to find the fastest route to your destination. Just like you'd want to reach your favorite coffee shop in the least amount of time, Dijkstra's algorithm works in a similar way. It starts at one point, let's say your home, and looks at all possible paths to reach the coffee shop. The algorithm keeps track of the shortest distance found so far and updates it whenever it finds a shorter path. It does this by adding up the weights, which in our case could be the time taken to travel from one point to another. So, Dijkstra's algorithm is like a meticulous planner, always looking for the best route. It's used not only in navigation systems but also in network routing protocols, and even in some games for pathfinding purposes. Just like Google Maps, Dijkstra's algorithm helps us navigate the complex world of graphs. Now imagine a journey with lots of stops, like a train route. Bellman-Ford finds the shortest path even if there are many intersections. Let's dive into the Bellman-Ford algorithm. Unlike Dijkstra's, Bellman-Ford can handle graphs with negative weight edges. It accomplishes this by relaxing the edges, which is a fancy way of saying it continually updates its estimates of the shortest path. Think of it like this. Bellman-Ford starts at the first station assuming that all other stations are infinitely far away. But as it learns about each station, it updates its estimates, getting closer and closer to the true shortest path. This happens over several iterations, each time getting a more accurate picture of the graph. But what if there's a negative cycle? That's a loop where the total weight is negative, causing an infinite loop. Bellman-Ford has a trick up its sleeve for this too. It uses a rule of thumb. If it takes more iterations to find the shortest path than there are vertices in the graph, there's a negative cycle. By being able to handle negative weights and detect negative cycles, Bellman-Ford is more versatile than Dijkstra's. However, it's not all sunshine and rainbows. This versatility comes at a cost, as Bellman-Ford is slower than Dijkstra's for graphs without negative weight edges. Bellman-Ford is the ultimate guide for complex journeys with multiple stops. As we journey through the world of algorithms, it's important to remember that each one has its strengths and weaknesses, just like Bellman-Ford. Think about transferring flights. Bellman-Ford helps in figuring out the shortest or cheapest path through different connecting flights. Much like a seasoned traveler, it navigates the complexities of air travel with ease. Let's say you're starting from New York and need to get to Tokyo. There are no direct flights and you have to make a few stops. How do you figure out the quickest or cheapest route? That's where Bellman-Ford comes in. It systematically checks all possible combinations of flights and stops to find the optimal path for your journey. Whether it's a stop in London, a layover in Dubai, or a change in Beijing, Bellman-Ford calculates all possibilities. It ensures you get to your destination in the shortest time or at the lowest cost. So the next time you're booking a multi-stop flight, remember Bellman-Ford. With Bellman-Ford, even the most complex journeys become a breeze. And that's how we navigate the shortest paths in graphs. We've journeyed through the bustling city streets with Dijkstra's algorithm, finding the quickest route from point A to point B. Then, we hopped onto the train of Bellman-Ford, navigating the labyrinth of intersections and discovering the shortest path no matter how many stops we had to make. These algorithms aren't just theoretical concepts tucked away in textbooks. They're the invisible conductors guiding us through our daily commutes, be it via Google Maps, or when we're catching connecting flights. And this, our dear explorers, is the beauty of computer science. It's always around us, silently making our lives easier. So, what's your take on these shortest path algorithms? Do you have any intriguing applications to share? We'd love to hear from you. Remember, each like, comment, and subscription fuels our journey deeper into the coded universe. If you found this route enlightening, comment and subscribe to Coded Universe for more tech explorations.